Welcome to DC Digital Learning Session. I am Shoban Kumar DM, working as Assistant Professor in Maharani Science College, Bangalore. Dear students, today we have discussed fundamental theorem of finite differences. In earlier classes, already you know that the meaning of finite differences. Meaning of finite differences: forward difference, backward difference, shift operator, central difference, and differential operator. Now we have to prove fundamental theorem of finite differences. Statement: the nth difference of a polynomial of nth degree are constant and all higher order differences are zero. In mathematically, delta raised to r f of x is equal to constant if r is equal to n. Here n is the polynomial, degree of the polynomial f of x, degree of the polynomial or degree of the function f of x. Here it should be 0 if r should be greater than n. That means the derivative here, this r is nothing but a derivative should be greater than degree of the polynomial. Now I have to prove this result. Let the polynomial of nth degree in x be the polynomial in this form. F of x is equal to a x to the power n plus b x to the power n minus 1 plus c x to the power n minus 2 plus and so on k into x plus h plus l. Here we know the definition of first forward difference. Delta f of x is equal to f of x plus h minus f of x. Therefore, here applying delta on both the sides, we get here, according to this ax to the power n becomes ax plus h all to the power n minus x to the power n plus b into here applying delta on this function, it becomes x plus h all to the power n minus 1 minus x to the power n minus 1 plus and so on. Last term is kh. That is equal to here and again expanding x plus h all to the power n, x plus h all to the power n minus n by using binomial theorem and simplify. We get a n h x to the power n minus 1 plus b dash x to the power n minus 2 plus c dash x to the power n minus 3 plus and so on k dash into x plus l dash, where b dash, c dash and so on l dash are coefficients of x. Thus, the first difference of polynomial of the nth degree is a polynomial of degree n minus 1. Similarly, delta square f of x is equal to delta f of x plus h minus f of x. And again applying delta on f of x plus h, it becomes f of x plus 2h minus f of x plus h minus of delta f of x is minus f of x plus h plus f of x. Here f of x get cancelled, f of maybe f of x plus h, f of x plus h may be cancelled, and remaining that is equal to a n h x plus h all to the power n minus 1 minus x to the power n minus 1 plus b dash into x plus h all to the power n minus 2 minus x raised to n minus 2 plus and so on k dash h. Now again expanding x plus all to the power x plus h all to the power n minus 1 x plus h all to the power n minus 2 by using binomial theorem and simplify, we get an into n minus 1 h square x to the power n minus 2 plus b dash x to the power n minus 3 plus c double dash x to the power n minus 4 plus and so on plus k double dash. Therefore, the second difference represents a polynomial of degree n minus 2. Continuing like this, for the nth differences, we get the polynomial of degree 0 because here applying the delta, here 1 degree is reduces. Here x to the power n minus 1, here x to the power n, after applying it, degree reduces n minus 1. And again applying delta on this function, and again degree is reduces n minus 2. so on like this. Applying nth derivative, delta raised to nth forward difference on this function, the degree should be 0. Therefore, here delta n f of x is equal to n minus 1, n minus 2 into 1 because the degree is 0. X to the power 0 should be 1 and h to the power n because here delta square, here h square, here delta, here h, like this, delta raised to n, here h to the power n. Therefore, here n into n minus 1, n minus 2 and so on, 1 means it should be n factorial. Therefore, delta n f of x is equal to a n factorial h raised to n. Hence the proof. This is required proof of the fundamental theorem of finite differences. It should be a constant, which is a constant. Hence, the n plus 1th and higher differences of a polynomial of nth degree will be 0. Will be 0. We note that the converse of the above theorem is true. That is, if the nth differences of a function tabulated at equally spaced intervals are constant, the function is polynomial of degree n. Hence the theorem. Now we discuss some examples. We are applying fundamental theorem of finite differences. Evaluate delta raised to 3 of 1 minus x, 1 minus 2x, 1 minus 3x. First, we have to simplify the given function 1 minus x into 1 minus 2x into 1 minus 3x. Here f of x equal to 1 minus x, 1 minus 2x, 1 minus 3x. After simplification, we get minus 6x cubed plus 11x squared minus 6x plus 1 plus 1 plus 1. Here f of x is a polynomial of degree 3 and coefficient of x cube is minus 6. It should be a naught. It should be a naught. And here h is a minus 1. H is minus 1 and n is the degree, n is equal to 3. Therefore, applying the fundamental theorem of finite differences, delta 3 f of x is equal to a naught, n factorial into h to the power 3. Here h is equal to minus 1. H is minus 1, minus 1 cube is minus 1. We get minus sign here. Okay, here minus a. Therefore, here according to this theorem, here h raised to n, n is equal to 3, minus 1 to the power 3 is a minus 1, and a is coefficient of x to the power n, is coefficient of x to the power n. Here instead of a, here a naught is minus 6, therefore h is minus 1, n is equal to 3, and we get delta 3 f of x is plus 36, not minus, here plus 36. Okay, this is plus 36. Plus 36. Because here h raised to 3, it should be minus 1, minus into minus, plus 1. I can write here once again. Here minus 1 to the power 3, minus 1 to the power 3 is minus 1 to the power 3 is minus 1. Okay. Now, and another example, evaluate delta n of 1 by x. Here delta n of 1 by x can be written as delta n minus 1 into delta of 1 by x. First, simplify delta of 1 by x. Here delta of f of x is f of x plus h minus f of x. Here h is equal to 1. Here let us take h should be 1. H is a width of the interval or step length. Here f of 1 by x is equal to 1 upon 1 plus 1 minus 1 by x. After simplification, we get minus 1 divided by x into x plus 1. Similarly, del square of 1 by x is minus 1 to the power 2 into x plus 1 into x plus 2. Here del of 1 by x is last term is x plus 1. Here del square of 1 by x is last term in denominator is x plus 2. Similarly, del n of 1 by x is minus 1 to the power n divided by last term should be x plus n, x into x plus 1 into x plus 2 and so on, x plus n. Here this is not n, this should be 2 minus 1 whole square, minus 1 to the power 1 minus 1 whole square, like this in the nth difference minus 1 to the power n. And next one, here delta raised to 10 of 1 minus ax, 1 minus bx square, 1 minus cx cube, minus 1 minus dx to the power 4. First, we have to simplify f of x. Simplify the f of x. After simplification, here in this part, here degree is 10. Here f of x is a polynomial. Degree is 10. Therefore, now applying 10th forward difference and fundamental theorem of finite differences. Here, this is a naught or a. This is a naught. This is a naught into h is 1. H is 1. And degree n factorial, n is equal to 10. Therefore, a, b, c, d into 10 factorial. This is the required result. I hope you are all understanding the fundamental theorem of finite differences and examples on that. Okay. Thank you.